Welcome back, Contemporary Math. We are in chapter 5D. We are going to talk about graphics in the media. So we're going to talk about a few different kinds of common graphics that are used and how to interpret them. So we're going to look at a bunch of different graphs and try to see what the graphs are telling us. So this section is pretty much all about interpreting graphs and visual representations. So if we look here, the first thing that they extend is the concept of a bar graph. So we can have a multiple bar graph, and it's an extension of a regular bar graph. And we're going to divide our set into sort of subsets. And so we're going to compare, like in this first one, figure 5.11 is a multiple bar graph. Part A is a multiple bar graph. Part B is a multiple line chart. And so we talked a little bit about how to do a line chart. You basically put a dot in the middle of the bar. So we could go from this to a bar chart, and vice versa if we had to. So what general messages are revealed via these charts? Okay. If we look at this one, there are hopefully two things you are getting from this. One of these, we're looking at the degree that's being obtained. So as this degree goes up, this is no degree at all. This is a professional degree up here. So with each iteration of the higher degree, you might notice people are generally making more and more money. So we have our bars divided into male and female, but you notice both of them are going up. So the lighter colored one is getting larger, and so is that maroon darker red color. And so that is telling me with higher education, there are generally higher wages. The other thing is there is a gender discrepancies here. So this, we can see the gender discrepancy. Women are making less than men across the board. And we can see the extent of it, right? We can see this gap here. We can see the gap between men and women for each degree level. So there is a difference in gender across all levels of education. So those are the two main things that I'm hoping you're pulling off of this first one. And this really helps us visualize it. So to put it in a split bar like this, we can actually see male and female sort of side by side within each of the classes of education, right? With this one, now this is a time plot. We are plotting time on the x-axis. We are plotting the different education levels of different colors. And we are plotting unemployment rate over here. So this is going from 0 to 10% unemployment rate in our y-axis scale. And we are going from 95 to 2016 on our x scale. And so what does this tell me about unemployment? So the education level, you might notice the color code is the same as the order of the colors here. So the higher educated you are, which would be this one, a bachelor's degree or higher. This would be not even a high school degree. So you might notice the more education you have, the less likely you are to be unemployed. More education. I'm putting extra letters in there for some reason. The more education typically results in lower employment rate. If we look at the unemployment rate here in 2016, so this is no high school and this is high school. So you might want to notice like this is a big gap. Finishing high school is going to greatly reduce the chances that you will be unemployed, right? Going from high school to doing a little bit of college without completing college, it's going to increase it a little bit more, but actually completing college is going to increase it a fair amount more, right? So you might notice that from going here to here. So that should also be telling us a little bit something about the degrees being obtained and how they kind of buffer us from being unemployed, right? So actually obtaining the degree is going to make a big jump. If you start school but don't obtain a degree, it will make a little bit of a jump, but not a very large one, is what that's sort of saying. Whew. And now this example. So what general messages are revealed by the graph in 5.12? Is this portrayed accurately in the graph? So one of the points they try to make in the book is that people will often like throw a figure out there like this, and this, just throw it out there. This is a bad figure. Like this is not a really well-drawn figure, and we'll go over a little bit why it is not a good well-drawn figure. But some people try to argue really sexist things, and one of the things the book tries to say is that people will try to argue that boys are innately better at math than females are for some reason. And this might be one of the things that they do, or one of the figures that they show you. And so we want to kind of explain why like this is a bad figure and why it doesn't prove what they're trying to prove. First off, these are the two things that I hope you notice. Finland, girls are scoring better on their math test, and in Russia, the girls are scoring better. So this, when we see the opposite point being proved in the numbers, right? If you're trying to say boys are better, they're not here and they're not here. So overall, we can't make some kind of generality that they are better, right? Because they're not demonstrating themselves here or here. This is actually demonstrating the opposite, that girls would be better. So with that said, what that implies is that it's probably cultural, right? It's a cultural thing that is happening. And if it's cultural or social, then it's not an innate sort of ability sort of thing that's happening, right? That would suggest not innate, that it's some sort of, it's nurture, not the nature, right? The other thing, and this is a big no-no, and we'll do this maybe a few times in the section. I mentioned it really briefly, but on your scale here, your scale should really start down here at 0. They're starting right here at 460. And why is that a problem? Well, let's imagine I move this up. So instead of starting at notice if I start deleting part of these bars, I'm only looking at this difference here. It's making that difference look larger and larger the more of this bar that I delete. So those bars look very drastically different in size, whereas those two look a little bit closer, right? So I can do that with a lot. If I just cover up half the bar, If all I see is those two bars, that one looks like it's half the size of the other one, right? So what you want to do is show the whole bar. And if we show the whole bar, it shows the whole proportion of the thing and not just the small little piece that you want to focus on. That is really deceptive. So what we should really do is we should really be starting at 0. We should not be making any breaks in our y-axis. So this is a big no-no. We should always start at 0 on the y-axis. That's a big no-no. Okay. The next graph is a stack plot. So a stack plot works really well when you kind of have pieces of a whole or something that you can subdivide. So we're looking here and we're talking about expenses in this graph. So if we're looking at expenses, we can look at overall expenses and we can divide it by a university or the type of university that you're going to, type of college you're going to. So they go with a public 2-year, public 4-year, in-state, and then a public 4-year out-of-state. So they're dividing the university by the type of college and by the type of in-state, out-state property, right? And whether it's public or a private nonprofit is the last one they have on here. So private nonprofit is going to be the most expensive. So if we want to look at the total amounts, this entire bar, ignoring the colors, is going to give us sort of the total amounts. And again, I don't think we had one before this. Oh yeah, we did. So I know I typically do my bar graphs vertically. They're doing them horizontally here, right? Which I'll have to deal with. It's not my favorite way to do it. But same thing here, right? They're doing it horizontally now. I prefer them vertically. I really like this vertically. But you don't always get what you want. The other thing is I have tuition. So I can look at tuition here. I can look at tuition here in the dark blue, and I can look at tuition here and tuition here. I can compare these things across the 4 universities. I can look at my light blue and look at the length of that light blue. And I can compare the length of that light blue. I can compare the colors across the 4 bars. And so I think yellow is bigger here than it is here and here. So that is telling me my transportation is going to cost more here than it will here. The green looks fairly consistent throughout, I think. Maybe a little smaller in this last one. So it tells you where your expenses sort of go. We can compare the expenses across the institutions, and we can just look at a single bar and look at where their expenses are going. So where's a private nonprofit 4-year on-campus student? Where is he spending his money? Most of it's going to be in that tuition in the $33,000, right? So this also gives us a sort of like proportional sort of breakdown of what's happening just within the individual's expenses. So what general messages or trends are revealed by the graph? Ooh, I talked about a few of them already. So these are divided by institution. So these horizontal bars are divided by institution. Their bars are further divided into categories of expenses. And so one thing is that it makes sense to put these things on top of each other, right? If we add this and we add this and we add this and we add this and we add this, it's going to give us the total expenses. So we're taking our total expenses and we're dividing it into subcategories. So if you want to show like parts of a whole, what parts of your budget are going to where out of the whole budget, this is a good way to do it. And we can compare those parts independently. We can compare the overall budget overall. And it gives a good visual to do that. Okay, another stack plot, but now instead of a histogram, or is that a bar chart? I think that was that one was a bar chart. It was by category. This one is a line graph. This is a stack plot, line graph. And so we're stacking lines. And so we're looking at this. So what general messages or trends are revealed by the graph in figure 5.14? So it briefly says what this is. This is trends in death rates for 4 serious diseases. So whether we're doing pneumonia, cardiovascular, tuberculosis, or cancer, we can look at these things, and it kind of says it here. But for the cardiovascular wedge, it's this beige sort of color in here. And we're looking here, this is 620, this is 180. If we subtract those two things, there's around 440 deaths per 100,000 people. So what we're actually looking at is the width of these colors here. And so what is this telling me about diseases? Maybe start with, let's go to the bottom up. Let's start with cancer. So cancer looks like it's going up until about 1990. And then it looks like it kind of sort of levels out after 1990, right? Not exactly leveling out, but fairly well. It looks like it might be even going down a little bit, but I'd probably just say leveling out. So it's going to go up until about 1990, then level out a bit. Tuberculosis, I can say that word. Tuberculosis. 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 No, I really can't say it. I was messing around for a minute. Now I'm really stumped. Tuberculosis is going strong here. You might notice it's shrinking and shrinking till about 1960. We don't even see it too much after 1960. Tuberculosis. You would say that's probably mostly eradicated, right? There might be a few examples here or there of it, but for the most part, it's not a disease we're looking at. So it became mostly eradicated around 1960. The next thing we want to talk about is the cardiovascular disease. So it looks definitely like cardiovascular disease is getting larger and larger until about 1960, and then it looks like it's getting maybe a little bit smaller. Increases, maybe even say slightly. It's not a big increase here, but it is definitely getting larger. And there's one other guy I got to talk about there. What's happening over in pneumonia land? So this is definitely a decrease in pneumonia. Until about where? 1950s? And it stays about constant. Maybe you would want to say it shrinks really slowly, decreases really slowly. It does look like it's getting smaller, but not quite as at a radical rate as that other one. And why does it make sense to stack these things? If we think about deaths per population, if we're going to stack this on top of this, on top of this, if we look at the four leading causes of disease, if we just look at this thing overall, ooh, one on top, this is going to give us, if we look along here and we look along here at any certain date, we can sort of pick off what the overall death rate is for all four diseases. So that is the other thing this sort of graph gives us a look at, is that we can look at the overall death rate when we combine all four diseases. And so when we start with all four diseases, I think we're getting around 800 deaths per 100,000 people. And so we can look at the death rate over time has decreased. So why I call it cardiovascular went up, while all cancer went up, tuberculosis went out of style, tuberculosis and pneumonia went out of style. I will say that word right eventually in these notes. So I usually don't have a problem saying that word. I don't know why. I just started tuberculosis. I started having a problem saying it when I did these notes for some reason. So let's go on. The next thing we want is a geographical data. So they're going to give you some sort of geographical data. So let's look at how this data is sort of presented. This is the per person energy use by state in gallons of oil equivalent. So units are gallons of oil equivalent. So it's color coded, and you might notice the bins. They are starting low here and going up. So states that are purple and green are using a lot of oil. States that are like this orange and yellow are using less. States that are this beige sort of color are using right in the middle. So they have the bins over here. They have the actual number on the state itself. It's a bit blurry, but if you print this thing out or go look in your book, you could probably see it. And this works well because we have sort of self-contained governments within each state. Each state has its own sort of energy usage. And so sorting these things out state by state really sort of makes sense. There are other things that maybe you can't sort out by state, like maybe weather or something along those lines. So that's where this next picture is coming from. We would call this a contour map. And so we also need to be able to read these contour maps. And so if we look here, we're starting at 20 degrees. So everything in this dark blue here is between 20 and 30 degrees. Everything in light blue is between 30 and 40. In the beige, it's between 40 and 50. And this orange is 50 and 60. In this peachy color, it's like 60 and 70. So we can see what sort of temperature these things are. Everything within the same color is going to be within the same sort of temperature range. So you get some kind of mountains out in here or something that makes a little bubble maybe in there, but we get this sort of contour map happening. So now the next few questions are going to be about looking back at these two graphs. So what sort of geographical characteristics are common to states with the lowest energy usage per person? So if we look at low energy usage, it's going to be all these states. It's going to be these orange states in here. And the yellows would be the second least. So what do those states have in common? A lot of these states, you might notice, are kind of southern. They are typically warmer states. So the book really says it's not, this is not something that is maybe easy to sort of recognize what's happening. But there are two sort of factors, is that they tend to be farther south, they tend to be warmer states, or densely, that's not spelled right. D-E-N-S-E-L-Y, densely populated is what they say. They are either warmer or they are densely populated. Which tends to make sense. Usually you spend a lot of electricity, a lot of energy to warm up your house during the winter. That's where a lot of the electrical and the energy usage is coming from. Part B says, were there any temperatures above 80 degrees? So this is coming from the questions on the next page. Were there any above 80 degrees? That would be these right in here. There's like this one color right in there. It says 80 degrees on the border. Somewhere in southern Florida. Yeah, it is happening. And then the other thing says, if so, where? We said that in the tip of Florida. What color represents temperatures from 50 to 60? If we're looking from 50 to 60, it is that orange color. I'm looking right here, all along here, all in here. And this is the 50 to 60 range. Okay. The next thing we want to talk about is three-dimensional graphs. So in one of the previous sections, I believe I gave you a country and I gave you CO2 emissions. So I think that was a previous thing that we had, something along those lines in the previous section. So we had two criteria. Now if we want three criteria, they're going to add a time element, they're going to add years to this. So now we're going to compare the CO2 emissions across countries, across the years. And so if we wanted to do that, we're comparing three different factors or three different variables. We would want to make a 3D graph of some sort. And we want to look at this based on figure 5.17 about when did China surpass the US in total CO2 emissions? Are there any noticeable trends for CO2 emissions? So if we look along here, these tend to be decent representations. This one's a decent representation, but one thing that can happen really quick when you're doing these sorts of things, especially with 3D graphs, is these are a little bit harder to read than 2D graphs. You're going to have to look here, you're going to have to look sort of along here, and you want to know when China and the US were about equal. It looks like right in here, these two bars are going to end up passing each other or being about equal. And what year is that? It looks like that's happening in 2005. So in this one, I think they did a decent job with their 3D graph. I think this is a decent way to do a 3D graph. But with that said, it is really easy to start putting in more variables, and it's not necessarily always helping your audience to understand the point that you're making. So is there anything else we want to maybe say? It looks like India, and this is also why. It looks like India and Russia caught up to each other somewhere along this line, right? Between 2005, 2010. It looks like Japan's been pretty consistent. They've gone up a little bit, but not a whole lot. So that's also something maybe we can notice. They have stayed about constant. So we can look across the color. Green represents Japan. All these orange represent Russia. All these yellow represent India. All these blue are the US. All these purple are China. We can look here along this line to figure out how much CO2 they're producing. We can look here for the year, and we can look here for the country. So there's a lot of information they're kind of portraying in this thing. Okay. Now we have an infographic that's just really hard to read. It's even hard to read when I look at my digital copy of my book. So I'm not really sure what to do too much there. But an infographic, as they say, one common type known as infographic, short for information graphic, generally presents a large interrelated set of information and data in a visual way with the goal of making it easier to understand and interpret all the information. So you're taking all your aspects of your design class and you're creating this sort of visual sort of representation in a really pretty way that attracts people's attention. This isn't always the best way to show data. It doesn't show things in a like numerically profound sort of way. It just like is a real eye-catching sort of thing if I'm being honest about how I feel. It doesn't really do a whole lot, but we want to answer these based on that infographic. What percentage of students feel their coursework is relevant to their life? So that might be something kind of hard to read on this thing since it's kind of blurry. But it says it right up in here. I believe it says 58% feel their coursework was relevant to their life. So I believe the 58% is what they're looking for. Can you draw any conclusions whether exercise contributes to a successful balance of academics and extracurricular activities? So it looks like 56% are saying that they exercise. And then we also know something, 79% feel they have, is this one right here, feel they have successfully balanced their academia and extracurricular activities. Academics. And so the book points out that if we're getting these large numbers, there's probably a good chance there's a sort of overlap in these things. This is 56% of your population, 79%. There's probably a good overlap, but without studying it, we really can't say anything else. Probably overlaps, but we definitely need to study more to understand how much they overlap, why they're overlapping, whether there's a mechanism for their overlap, which may not be too crazy of a thing to sort of talk about here. We really cannot draw any more conclusions. We can say these two things, but we can't talk much about their overlap without getting more information. Okay, with that said, the next thing we're going to go through is a few cautions on graphics and basically what not to do with your graphic. So this is a perceptual distortion. So this goes back, oh boy. If I have a length of 1, and now I make this length 3, what does that do to my area? So in the first dimension, it's 3 times. You might notice in the second dimension, it gets to 9 times. And in the third dimension, it would be 27 times. So when we triple a length, we are doing it by a factor of 3 squared for the second dimension, and we're doing it by a factor of 3 cubed for the third dimension. So we talked about this dimension analysis sort of thing. That is what is coming into play here. So now if we go back and look at these bills, this is 34 cents, this is $1. So they're trying to compare these two amounts over time. And so I want to ignore this right picture right quick. I just want to look at this picture with these dollar bills. So 34 cents is about 33 1/3. It's about 1/3 of this one, right? So if this one is 3 times, and what they're doing is they're taking this right here and they're putting this 3 times the length. So if we look at the length is being multiplied by 3. But when we look at this picture, this is a 2D object. Our eyes are not drawn to the length of this object. If we want to compare the size of this dollar bill to this dollar bill, what our eyes are going to typically do is they're going to compare the size or the area of this thing. So what we actually have is, if I can draw it, not a straight line at all. We actually have 9 of these bills up in here. So this thing looks like it's 9 times as large as this. So that is a distortion of what is really happening here. So when we do one dimension, you should really keep it one-dimensional. So these things are perceptual distortions. How does the length of the $1 bill compare? So it's about 1/3 of the length, but it's about 1/9 of the area. Or one is 3 times as more. Same as saying the other one is 1/3 of the other one. You could also say 3 times the length is 9 times the area. That would also be a correct and good statement. So that is the left one is the one that they give you in the book. This one is one I found out in the interweb somewhere. It was a bit hard to find a source on. I don't think the person that wrote this up wants to be found. This is not a good example. But one of the reasons, this Latvian lady's about to crush this little Indian lady with her pinky toe, it looks like. So hopefully she doesn't step on her. What they compared, and I think this is getting at the same concept, plus they have something even more wrong with this one. This is getting at that same concept where if we increase it by a single dimension of height, we're increasing the area of these figures by a square of whatever this is, right? Whatever multiple this is, we're going to have to square that. So the area of these things is not increasing at the same rate that their height is increasing. It goes back to the dimensional analysis. The other thing is I'm not starting at 0 there. So that's another thing that is making these things look way larger than they really should. So I threw this in there because I think it's kind of a funny graphic. It looks like this lady's about to squish that lady. But that's what happens when you don't draw your pictures correctly. People get scared they're going to get squished. So that is one thing you don't want to do. So don't start drawing things with areas when you're only comparing one dimension. The other thing we want to talk about is scaling. And so for right away, big no-no, right? They're not starting at 0 there. So first off, that's already a big no-no. Don't do that. The other thing is their scaling. So we're going from, what, 30 to 60. If we're doing women as a percentage of all college students, and it says it down here, but these are the same graph. They're just changing the scaling on your y coordinate. So here, this is the one that you really want to do, right? This is the one that's the bad example. So this one, we're starting at 0. We have all our intervals are evenly spaced. So you want to make sure your intervals are evenly spaced. And you want to make sure your scaling kind of makes sense. So we're going from 0 to 100. We're talking about percentages. So it's going from 0 to 100%. This gives us a good visual representation of what is really happening in here. So depending how far you zoom in and out on things, you could really exaggerate sort of things going up and down, right? Versus what they might actually look like. So when we zoom in, we get a lot steeper sort of valleys and peaks. Versus when we zoom out, we get a lot of better overall sort of behavior of what's happening here. So here, these increases look really, really drastic. Here, they look less so. Now we want to talk about a nonlinear scale. So we're looking at this thing. And if we look at this thing, we notice it doesn't increase much, and then it just like starts shooting off. It just like increases crazy amount. So over here on the right, if we notice our scale, it's going up by the same amount each time. So this is a typical linear scale over here. Okay. What this might remind you of is this is increasing really, really, really drastically. Another word we use to mean that things increase really, really drastically is exponentially. So this is actually, if you graph an exponential function, this looks very much like an exponential function. It starts off really slow and it just picks up crazy amount. And so I'm thinking that looks like an exponential shape. And so if I want to change my axis to exponential sort of things, what I'm changing my axis to is things of base 10 or 10 to the x. So 10 to the first is 10. 10 squared is going to be 100. And so I'm going to increase by a power of 10 each time. And so if I want to change my scale to an exponential scale, it's going to look like this. And so each time I'm multiplying by 10, I'm adding another 0 to my number. And so this is the same graph with a different y scale. This one is linear scaled, and this one is exponentially scaled. Okay, so when we account for the exponential, it ends up giving us something that looks more sort of like a straight line. And which graph in figure 2.1 can you use to determine how many times faster the record supercomputer was in 2000 than in 1970? Use your answer to comment more generally on when exponential scales are useful. So exponential scales are useful on things that look like they might be exponential. We can put it into an exponential scale and see if this thing looks a little prettier. So if we want to figure out what supercomputer speed was in 1970, if you want to do it with this one over here, good luck. Try to figure out what that amount is. You're probably not going to see it. The 1970 was right around here. What I'm seeing is it's about 10. If I look over here at 2001, we're at 2000. Where am I getting here? It looks like it's around 10 million. Okay, so in 1970, we get about 10. And 2000, it looks like it's about 10 million. So how many times faster was the record supercomputer speed in 2000? So it was 1 million times faster. We went from 10 to 10 million, that's 1 million times faster. We would have to multiply by a million to get from 10 to 10 million. So which one is easier to grab a number off of? It's much more easier when we make our scale exponential when our graph looks exponential. If we're making our scale look like a linear sort of scale here, it's going to be really hard to pick numbers off of this thing because these things increase so drastically here and they're so close together here relative to how far away they are here. So if we make the scale exponential in nature, then we can sort of get these independent sort of numbers out of here. And we can tell how many times this thing is increasing. And so these are for things that are increasing in an exponential fashion. We didn't go over that section. That is, I believe, chapter was that in the book that does that? There is one in the book. In chapter 8, they start talking about exponential stuff. Okay. So that is example 9. And we have just, I think, 2 more. Yeah, we got percentage change graphs, and then we got pictographs to talk about. Okay, so we have these 2 graphs. This one is changes in college tuition. They're comparing public to private with the 2 different colors. And here's the actual cost of tuition. And they're comparing public to private with the 2 different colors. So for the time period shown in figure 5.22, in what year did public college tuition increase the most? So if we're looking at public, we're looking along here at the purple. And where did it increase the most means where is the highest percentage of increase that happened in there. So if we want to know where it increased the most, you could try to compare purple bar to purple bar over here, but that's going to be really difficult. And so we don't really want to compare the purple bars. I think it's easier to compare the changes that happened. And so we compare the changes, we want the most change, which happened right here. It looks like 03 to 04. Okay, so in 03 to 04, it increases the most. And then when is it going to have the highest tuition? Well, that's easier to see, I think, over here, where it shows you your overall tuition. So when is that tuition going to be the largest? It looks like probably the last years that they're giving us, 16, 17. It's only going up and up. So 16 to 17 is going to have your highest tuition. All right, and then the final graph we want to look at is a pictograph. So sometimes they like to put a bunch of pictures on a graph and a bunch of graphics. Sometimes they're meaningful, sometimes they're not so meaningful. So we want to look at this graphic, and they ask us, this says world population in billions of people. We see all these people, we see the earth, we see all these good graphics, we see this little bar chart. It looks like this is the year under it. They don't really tell us what these numbers on top are, but they are the population in billions of people. So it's not really super obvious that that's the population that's on top. It's not the best organized graph, if I'm being honest, right? They could have gave us a scale over here, maybe. So typically in a bar chart, we have our scale over here. 1, 2, 3. All right, usually they do a scale over here, and usually we do a scale over here with equal years. So there are a few things to gripe about this bar chart. Discuss what aspects of the pictograph represent real data and which are statistically meaningless. So the real data is the year, the population, in billions, and maybe the bar itself. The length of the bar is accurate to how large the population is. So those are basically the three pieces of information that they're giving us. They're giving it to us in a really weird way, right? Sort of like I made that sentence. Discuss which aspects of the pictograph represent real data. The year, the number on top, and the bar are what really represent the data. The earth, the people around here, all this other stuff is just fluff. So why is it misleading? I would say because usually you have a y-axis and you have an x-axis. And the thing about your x-axis is that this is usually consistent. If I'm going 1990 to what, 2000 here, my next one is going to be 2010. My next one is going to be 2020. I'm going to keep going up by the same amount. So if I have a consistent scale here, this really helps me to see the growth over time. This does not help me so much to see the growth over time because I didn't look at how many years, but 1927 minus what, 1804. This is one thing you don't want to do. You want to keep the amount that you go up the same every time. That's not what they're doing here. And they're not spacing these out accordingly, right? They're not doing it. They're not spacing them out, what's that? Vertically, horizontally, in the right sort of spacing, right? So between those 2 years is 123 years. Between 2024 and 2040, I think this is only 16 years. So here we have like 120, here we have 16 years. This is really distorted on its x-axis, on its time axis, right? So that's not really showing you what it's doing over time very well. It looks like a consistent increase over time, and it's definitely not. And it looks like a consistent increase, mainly because we're not doing our axis the way we should here. Okay, so that is it. That is the final pictograph we're going to look at on the section. I hope you all take care and see you.